There we go. All right, so the most powerful activator is going to determine our substituent placement. So how do we know what the most powerful activator is if we don't have that table sitting in front of us?
Well, I mean, we kind of already know the habits. Like,
Right.
we know anything with an X is like a gray area, but if it is like oxygen or carbon, strong. We need it fast.
So oxygens, anything with a lone pair conjugated, especially an oxygen or a nitrogen with a lone pair, is going to be strongly activating. R groups, like with carbons, are weakly activated. Because the ones with the lone pair that are in row 2 of the periodic table can donate via resonance. But our R group can only donate inductively or through hyperconjugation, if you remember that term, when we first talked about carbocations. So our oxygen is going to be more strongly donating. So if we're trying to add a nitro group, strongly donating is strongly activating, which means OP. It can't go in the para position because there's already something there. So in this case, it would have to go in the ortho position.
So then for most power, like to determine that it's gonna be anything with the lone pair, what if there is one with the lone pair? Like what would our next? What would we look for next? If we like didn't have it.
If we didn't have a lone pair, then this is weakly activating. If it doesn't have a lone pair and it's not an R group, it's probably electron withdrawing, because for the most part, that means you're going to have a conjugated pi bond. So for instance, if we had an NO2 group, if I draw the whole thing out, looks like this, which means conjugated pi bonds. Conjugated pi bonds are electron withdrawing. And if it's electron withdrawing, that means it's going to be deactivated.
Okay, so I'm just trying to like think this steps, right? So we first look and see if we have a lone pair.
Yeah.
So if we don't have a lone pair, we're looking for our R group.
Exactly. If you don't have an R group, you're looking for a halogen. And then if there's no halogen, you're looking for conjugated pi bonds. That's going in order from most strongly activating to most strongly deactivating.
And what would that then look like?
Conjugated pi bond. So activating at the top, deactivating at the bottom. So if I was going to sum up that entire thing in one, as concisely as possible, I would do something like this. And just remember that you're activating. There's your line between activating and deactivating. And everything here and up is OP, and conjugated pi bonds are meta.
That means oxygen and nitrogen is, and the OP is the.
Can't you tell that's a lowercase though? No, yeah, you're absolutely right. This is oxygen. I just wanted to distinguish oxygen nitrogen lone pairs behave differently than halogen lone pairs. So let's try it with our abbreviated table here. We're doing a Friedel-Crafts acylation. Acetyl chloride is CH3. Is acetic acid, but you pull off the OH and you base it with the Cl. So for each of these, the arrow would look like this. Doesn't have lone pairs. Sometimes you might have to draw out what that group actually looks like to remind yourself what you're looking at. But if we're starting with them going down, yeah, no lone pairs on them. It's not an R group,
It's not,
not a halogen.
well, oh, but it does have conjugated.
It has conjugated pi bonds. So you don't have to start at the top and work your way down if you can recognize it off the bat that it's got pi bonds or something. Yeah, so we've conjugated pi bonds, so it's strongly deactivating. So it's going to be meta. Bromine's a halogen. It's weakly deactivating, but it is the one, halogens are the one that are in that gray area where they are weakly deactivating, but they're still OP. So we could have our acetyl group back here, or plus. I'm not sure where I write or because we don't do that in chemistry. All right, so the third one. We just determined NO2 is meta. The OH is strongly activating because it has lone pairs. So it's orthopara. So do these work with each other or oppose each other?
But they're like, it's gonna go with the constant OH.
So the
No, it's era.
so are they working against each other? One's activating, one's deactivating. Yeah, exactly. So then I guess I was ambiguous with my phrasing. They're working against each other in the sense that one's activating, one's deactivating. However, they're both deactivating and deactivating, both trying to put the sub in the same carbons. So in that case, we can consider them as working together.
Why do you have two blue ones?
Because there's two positions you can add. Let me clear the purple ones and I'll draw the both products. So we can put it there because that's ortho to the OH group and meta to the nitro group. We have another position that is meta to the nitro group and is para to the OH. So these OP directed, for a lot of these, there's going to be multiple possible places to put it. The reason we didn't get two products here, there's still two meta carbons, but both will give us the same product because we wind up with symmetry and being able to just flip it around. For these ones that are more complicated, you can wind up with two different products based on placement.
They both have lone pairs.
They both have lone pairs, so they're both strongly activating. Are they working together in terms of the placement?
They're in one baseball opposite ones.
That one, orthopara, right? What's orthopara for the methoxy group? Right? What about for the OH group? What's ortho and para for the OH group? So they are agreed.
So this one gives us 3.
This would give us 3. Yeah, because we don't have any symmetry anymore, right? We could put it in between the two of them. We could put it opposite of methoxy, but ortho to the OH. We can put it para to the OH, but ortho to the methoxy. Have you come around to the cult of the Swiffer?
Not really.
No.
She uses it like sometimes, but I think she's traumatized from her first ever day of teaching. Because she says her very first day as a teacher was teaching at a university indoors.
Mhm.
And she used like the spray expo stuff.
Oh yeah.
And then she was like, I couldn't write on the board the rest of the class because like it was still wet.
Mm.
And so I think she has like, doesn't like,
Class for sure.
yeah.
Yeah. It's okay. I use one of those exo sprays on the painted whiteboard upstairs on the art that's there 10 years later.
That was you?
That was me.
The new one?
The one, it wasn't 10 years ago, but it's probably 8 years ago now at this point. That was the first room that they redid when they were testing this new technology and new setups for the classes. And when they painted the whiteboard, somebody left a mark on it. I think somebody used a permanent marker on it. Like the first week that we had it painted there. So I mean, well, the spray should remove that. So I just put the spray on it, but the spray couldn't finish off too.
That's insane. That's such a bad design.
It was not great. It was designed by a guy who'd never taught before, who doesn't work here anymore. Yeah, there were a lot of issues with that classroom. There were some good things I like about that classroom, but not the whiteboard anymore. All right, let's do 2 more, just because we should review. At least with these ones, we don't have to worry about ortho, meta, and para. We're starting from benzene. What if we had excess? Well, fuming sulfuric acid pretty much always have an excess of it. But it usually stops after one step. Why might that be the case? Might be helpful. If I draw this out.
Stairs.
No,
No?
not this time. Where does that group fit on our chart over here?
Conjugated.
It's conjugated pi bonds, so does that make it?
It's gonna be meta.
It's gonna be meta and strongly deactivated. So basically, the reaction slows down so much after the first step, if there's nothing else attached to it, you're really only gonna have one solvent group. So if we had a methyl group or an OH on here, we could continue on because then we have a strong activator controlling things. But if we don't have a strong activator, all we have is a strong deactivator, it'll stop after one.
For both of them?
No,
Means
it's a halogen, which means it's deactivating, but weakly. It's OP.
I think just given what we dealt with bromine before, it's just
It's gonna add more, at least one more. When you've added 2 bromines, now we will end up in the case where, okay, yeah, it's weakly deactivating, but we're deactivating it twice.
Yeah.
But we can do it twice. So it's weakly deactivating, but it's orthopara director. So where can we put the next bromine?
right next.
Or that. And they would probably stop there no matter how much bromine you have, in all likelihood. There's probably a way to make hexabromobenzene, but I don't think we could use this mechanism to do it. All right, I've got a whole nother page of practice with these, but we'll save it, see if we have time. In the interest of making sure we get to our finishing our lab today. So let's talk about our 2 new mechanisms. First, we're going to talk about its nucleophilic substitution, but it's aromatic nucleophilic substitution. So it's going to have a whole different set of rules because SN1 and SN2 didn't have any aromatic character to them. We hadn't talked about that at all yet. And so this is going to behave really differently. So a nucleophilic substitution is still going to be somewhat similar to what we saw before in that we're replacing a leaving group that's not hydrogen. We're not replacing a hydrogen this time, so we need a good leaving group. And if it's nucleophilic, we also need a strongly electron withdrawing group on there. Because if it's nucleophilic, we have to give our nucleophile a place to attack. Benzene rings have a lot of electron density around them, which is why electrophilic reactions work. But if we want to do a nucleophilic group, we have to have an electron withdrawing group to pull that electron density away and sort of expose the carbons. Right, so powerful electron withdrawing group. Nitro group is the standard, but anything that's in that strongly electron withdrawing category could work. Good leaving group, as we've usually seen with SN2 and SN1 reactions, halogens are our go-to, especially bromine. The third criteria is the trickiest one. Well, it's not really that tricky. It's similar to the ortho-para directing logic. It has to do with the resonance structures. We need the leaving group has to be ortho or para to our electron withdrawing. Because if we have this nitro group, if we have a nitro group attached to a benzene ring, any conjugated pi bonds are going to have the ability to have a resonance structure that looks like this, right? That positive charge can resonate around to the ortho and the para positions. The fact that the positive charge can be on the ortho and para carbons is what's going to make it a good target for a nucleophile. We need something that has some partial positive character in order for a nucleophile to attach to it. So that's why these only work if your leaving group and your nitro group are ortho-para relative to each other. And so if we have a nucleophile attached to that to this position here, if we bring in hydroxide as our nucleophile, we need to make room for it, right? And that's going to put a negative charge. So it's going to look kind of like our sigma complex. Our sigma complex, we brought in an electrophile, somebody who was missing electrons, and then we wound up with that resonance structure where we had a positive charge resonating around. Except now we're not bringing an electrophile, we're bringing something with a negative charge. So now it's not going to be a positive charge resonating around the ring, it's going to be a negative charge resonating around the ring. Right, so they don't call it the sigma complex. Sigma complex specifically means that it's a positive charge. They call it the Meisenheimer complex. Right, so our first step is nucleophile attached, where your leaving group is attached. And that gives us this Meisenheimer complex where we have this negative charge that can resonate around it, like we were just talking about. Which doesn't really disrupt, it kind of disrupts the aromaticity temporarily. Because think back to Hookel school. We had 3 criteria for something to be aromatic, right? Do you remember what the 3 criteria were? Correct.
Number of pi bonds.
Good. The first one is the simplest one. You actually folded it into the first one you said. Conjugated all the way around the what?
Ring.
So it has to be a ring.
Okay.
Has to be cyclic.
Right.
Has to have pi bonds conjugated all the way around. And then you have to have an odd number of electron pairs. Is this one conjugated all the way around?
But have lone pairs.
That carbon is sp3 right now. It's sp, the carbon's sp3, it can't participate in resonance.
Yeah.
So we've got all these different resonance structures, but that one carbon can't be part of the resonance structure because it's sp3. So we broke the aromaticity temporarily, just like what we did with the sigma complex. So the next step is your leaving group leaves, and that lets you make the aromatic ring again. Right, so the nitro group has is the use of the nitro group is twofold here. One, it gets us, remember our sigma complex only had 3 resonance structures that we could work with, right?
Yeah. This is cool.
This has 4. That makes it a little bit more stable. And by pulling electron density away, that's what allows us to put a partial positive in the ortho and para positions. Right, so it works, it's doing 2 things here. All right, so let's try practice. We have 2 good leading groups. We have a nucleophile. We have a nitro group, and we have 2 good leaving groups. How do we decide which leaving group gets replaced and by what?
Electron.
No, not this time.
The ortho.
That one. So the chlorine or the bromine is ortho or para to the nitro group. Bromine's meta to the nitro group. So the chlorine is para to the nitro group. So the chlorine gets replaced. So nitro group's still there. Bromine's still there. We replace the chlorine with what? Not in this case. Close. What part of that, what is that really? You break it up into its pieces. You get Na plus.
Yeah.
And a methoxy.
Okay. So just the methoxy.
Yeah, so we're gonna get, this is our nucleophile, right? The sodium's just there to balance the charge.
Yeah.
Okay, different type of review.
Okay.
What's the common name for that molecule? It's okay, I had to double check myself, but I was remembering properly.
Well, okay, we know that's a methoxy.
Mhm.
And benzene is the other common name.
So you could call it methoxybenzene. Methoxybenzene, that's actually how I double checked the common name, was I typed in methoxybenzene, and what comes up is
Benzoxy.
anisole.
Oh. We usually have to know.
That's one of the ones that's less common. I was just seeing if anybody did remember it. Right. So for one of the really common ones, I want you to know like toluene, phenol, those ones, but for sure, I want you to know the common names, but if you couldn't remember anisole and you came up with methoxybenzene, I probably wouldn't mark you down.
Your dad, you fail.
So if we know this is anisole, how do we name this?
With aerosol in the name. What, wait. 4 nitro, 2 bromo. Wait, what's the aerosol? That's what I mean.
Yeah. that's gonna be our IUPAC name. If you wanted to name it as methoxybenzene, then that means you have to say when 1-methoxy 2-bromo 4-nitrobenzene.
Yeah.
Would also get you to the same thing and also be an unambiguous way of naming it. It's just more syllables. So when you can remember the common names, it's a good shortcut.
So we start with the regular benzene.
Starting with regular benzene.
And we think that
We have any electrophilic aromatic substitutions that involved an NH2 group. This is one where there's a couple of right answers.
I don't have an N over two.
So there is a reduction reaction to take a nitro group to an amine group. I don't think we've covered it yet though. So let's not use that one.
Okay.
So we can't just put a nitro group there. We can put, we have a reaction, do we have a reaction to put an OH group?
But like, we want one of the ones that we just learned like this last, right?
Would make sense. We have a way to do it. If we started from benzene,
Yeah.
let me draw our target over here so I can light up the board here.
I want to see like add then double on into like the carbon chain at NPH.
Sorry, say that again.
The only one that I have is a double bonded oxygen to an ethyl group and then adding NAPH4.
So we can take that and we can reduce that. If we're trying to get to this, we don't have a reaction that just has an OH either. But we do have a reaction that allows us to replace a bromine with an OH that we just learned.
Oh, yeah.
We could do that step, right? That's the one we just learned.
Yeah.
We could take a bromine. We have, if we have a nitro group para to a bromine, and we expose it to a strong nucleophile with some heat, we can do the nucleophilic aromatic substitution. So how can we get from benzene to Q?
Okay, well, I know that we can add the bromines by just doing Br2 times iron.
Fe is iron. So
If we're starting with just a blank rate. Br2 and take the bromine off. CHM223. CHM223.
Yeah. And that actually takes us all the way here, right?
Yes.
Because the bromine, well, let me back up. Both of these reactions work on a blank benzene, right? Does the order matter?
Oh, well, yes, because the bromine is a halogen. So it's gonna make sure that the NO goes, I mean, where the order in this case we want.
Right, so we get a 50-50 mixture. We get some mixture of the ortho and the para products. If we did the nitro group first, one is the deactivated group, which makes the next step slower.
Yeah.
It might still happen, but we want to avoid that. We can use a weakly deactivating group first. It's also an ortho para director, allows us to put the nitro in the right spot. So we'll get some of this. Luckily, bromine is also large sterically. So that probably helps us. It's a reason to use bromine instead of using chlorine for sure. So that gets us to here. We're still one step removed. I think we talked about it when we talked about hydrogenation reactions, but we didn't really have any use for nitro groups at the time. So we didn't really emphasize it. If you do the same thing as we would do to hydrogenate an alkene, hydrogen gas and platinum, or there's a couple other catalysts that work. My notes say palladium or nickel also work. But either way, you can reduce a nitro group to an amine group to an NH2 by just adding hydrogen gas to it with the catalyst. So our final product and so in both of these cases, we put a functional group in the spots where we wanted it, and then we converted the functional group to something else.
Yeah.
Right, and the order of the steps does matter, not just for over here, meta versus para, but we can't reduce the nitro group until after we do the substitution reaction. Right, because we need that strongly electron withdrawing group in order for this step to work.
But why didn't we just end this?
Because the problem said NH2, not NO2.
Oh.
All right, we good?
Yes.
All right, last mechanism for this chapter. This one's called elimination addition. So it's a similar net result to our nucleophilic aromatic substitution. It allows us to replace a chloride or a halogen with a nucleophile. But it's not the same as the other mechanisms we've seen. So specifically, we need a nucleophile. We need to get hot. But then we also follow it up with acid. Right, and the reason that this works, the reason that the mechanism is different, it can't just be a regular electrophilic aromatic substitution, Because if we do this on a toluene, on chlorotoluene, instead of just benzene, we get two different products, but they're not orthopara. So all of our mechanisms so far, it's either orthopara or it's meta. This one allows us to get the para product in the meta, which is weird. Tells us that something different must be going on.
Yeah.
All right, so with the way they go ahead.
Which one is the elimination condition mix? The ones on the top or the one on the bottom?
Both. So these are both elimination, but you can switch out what the nucleophile is to get a different product. If we use any OH here, we put an OH there and an OH here.
But you also switch out the heat for. I think.
So if it's not OH, you don't need the heat as much because this is a much stronger nucleophile than hydroxide is. It's a stronger base too. So let's talk about why that works. Right, so the way they figured this out is because they made a benzene ring, a chlorobenzene, where you put carbon 13, specifically where the chlorine is attached to it. And when they did this reaction, they found out that we're not just putting our new nucleophile on the same carbon that had chlorine.
Carbon 13 or 14.
14. Okay, sorry. It works the same way. For whatever reason, they used carbon 14. They could have used carbon 13. I don't remember why. Good catch. The important part here is not which isotope we're using. It's that we could tell that our new nucleophile is getting added 50% of the time. It's getting added to the carbon that had the chlorine attached, and 50% of the time it's getting added to one of the adjacent carbons, which is weird.
Yeah.
So our best explanation for how this happens, the one that fits all the data, is that we actually do an elimination reaction first. And that's why the heat's necessary if we don't have a strong enough base. Because if you heat and it's something that could go through multiple reactions, it's going to favor the mechanism that makes the most entropy, right? So it's going to favor the elimination if we heat it up enough. So it goes through this intermediate called benzyne. Basically, if your nucleophile is strong enough base as well, it'll actually pull off a hydrogen from the adjacent carbon. And when it does that, now we have a carbon with a lone pair. And that lone pair can't participate in the resonance, but it still gives us a carbon with a negative charge. And as long as we have a good leaving group, it'll basically kick off the leaving group and we make a triple bond. All right, so this is benzene. It's benzene, except one of those double bonds is actually a triple bond. And it's still aromatic. Even though we now it looks like we have 4 pairs of pi electrons, it's not anti-aromatic because one of those pairs of pi electrons can't be part of the resonance because it's 90 degrees from everything else. So if we were trying to draw what the orbitals look like on this, remember benzene basically has like a donut shape.
Yeah.
Right, on top and bottom. Well, and then the carbons. Basically, what we're getting here is another pi bond that's sticking out sideways where the hydrogen would normally. So that's not going to resonate, just like a lone pair. It's not going to resonate if it's already got a pi bond. So here's the example of what the orbitals would look like. Our red and our blue d orbitals are the ones that are part of the aromatic ring. The green ones are rotated out to the side so they can't resonate because their carbon that they're attached to already has pi bonds participate. Right, so that's the only reason why this can even happen without becoming anti-aromatic, is because we get that extra sort of 90-degree angle. Right, so the name of the mechanism is elimination addition. So what do you suppose the next thing is going to be? Yeah, an addition step. We have an extra pi bond that's not affecting our aromatic characters. That extra pi bonds can just go through a normal addition reaction. So that's why the second step is add acid. Because the first thing that's going to happen once we make the benzyne. So here's our complete mechanism. Nucleophile acts as the base to make the benzyne, and our leaving group leaves. And then our nucleophile comes in and attacks one of those two carbons in a regular addition reaction. Right, so the reason that we got two different products, the reason why we didn't just substitute it where the halogen was, is because once you get to benzyne, either of those two carbons is equally good as an option for our nucleophile to attack. So it just picks one at random, so you get a 50-50 mixture. So obviously benzyne doesn't look like a super stable molecule. We don't like sp carbons in a ring structure because they're supposed to be, sp carbons are supposed to be 180 degrees, but this benzene is stuck at 120 degrees, just because of the geometry, right? So when this was initially proposed, everybody thought that's a little far-fetched. But if that's true, if benzyne actually exists, we should be able to allow it to go through other reactions that are similar to other reactions that alkenes can go through. And so they actually put it through a Diels-Alder reaction. You can actually make benzyne, and you can't isolate it, you can't store it and put it on a shelf, but you can make it, and it lasts long enough that it'll actually go through other pi bond reactions, like a Diels-Alder reaction. So it can act as a dienophile to go through a cycloaddition. Right? So we haven't talked about Diels-Alder in a month now.
I like to go.
Yeah, the way that Diels-Alder worked was we just needed a pi bond. Ideally, it had some electron withdrawing groups around it that could react with a dienophile, or sorry, react with a diene. And so this fit the bill. So we can actually, this is a pretty good indication that benzyne exists, even though we can't isolate it, because it's the only way to explain the fact we can make this molecule. Right, so this is our only reaction so far that doesn't go through that, let's break the aromaticity and remake it, sort of intermediate. Right, our electrophilic aromatic substitution did, and our nucleophilic aromatic substitution both went through their own version of a sigma complex or Meisner complex. This one doesn't, but really it is literally an elimination reaction to make a pi bonds, and then you do an addition to that pi bonds. So it's a specialized niche circumstance that allows it to exist, and we make a weird intermediate, but it does kind of make sense with the reactions we've learned so far. So let's look at this one. I don't think we'll do the synthesis reaction today, I don't think. Just because we're coming up on an hour here. You have 4-chloro, 2-methyltoluene. You can treat it with sodium amide followed by acid. So let's draw out what that looks like so we can see what we're dealing with here. So that's our methyl for toluene, 1, 2, 3, 4. So we could also call it para chlorotoluene, chlorotoluene. And our arrow is going to look like
Do we have another method?
oh, yes, we do. Thank you. So is this one of our electrophilic substitutions that we did last week? That we started on Tuesday too. Good. And is anything about this missing electrons? I mean, the sodium has positive charge, but we haven't seen sodium act as an electrophile. That's not an electrophile. It's a nucleophile. So the fact that we have a nucleophile means it's not going to be our first mechanism we talked about today. And it's not going to be the nucleophilic substitution. Why not? There were 3 criteria for that one, right?
We need to have a good
Do we have that?
Yeah.
No.
a good leaving group.
We do have a good leaving group, but we don't have a good electron withdrawing group, and if we don't have a good withdrawing group, we can't have it para or ortho. So that leaves elimination addition.
Yeah.
So we're going to make benzyne. We have strong base and a good leaving group. So we do the elimination first to make the benzyne.
We can just skip straight to that.
Just because it says draw both products, it doesn't say draw the mechanism, but if we wanted to draw the mechanism, we would actually draw it as those electrons stay here. So we would get a negative charge here. And when you have a negative charge adjacent to the chlorine can get booted. It's not really getting booted off, it's taking out electrons with it. There's a benzyme intermediate. Why did I draw the nitrogen or the nucleophile pouring off the hydrogen from this carbon instead of that carbon? There's the hydrogen there too, right?
We always try or
To the leaving group. But both of these carbons are orbital to the leaving group, aren't they?
so that's the one that satisfies both. One the
This one is a, we don't need to satisfy both because we're not talking about cryptoparadiracs. We're just talking about what's an adjacent leaving group, what's orbital to the leaving group. That one's more of a leader, so that they're both good targets.
But because the one's closer to the methyl group, and it will have this.
It's maybe there's a little bit of a steric hindrance there. But we're really gonna see. Both of these. Which they don't look all that different. But this one gives us the ability to put something adjacent to the methyl. This one, both of these carbons are identical. They're both meta to one methyl and para to the other. So anytime you go through elimination addition, you're gonna have to look at both possibilities for your benzyme intermediate. And see if they're both valid. In this case, they are. And yeah, maybe this one gets favored a little bit because of the sterics, but methyls aren't that big. If it is a T-butyl group, then maybe that might make a larger effect. Or if we had a sterically hindered base, if we use T-bu-OK, that might affect it as well. But in general, we're going to get both possibilities if there are two distinct possibilities. So then the next step, the addition step. Same base is going to then act as our nucleophile. And it's going to break that extra pi bonds. So our NH2 can come in here and it can attack here, or here, or here. Do I need to draw an arrow to that one too? It's the same as that one. So if we attack, I'm just going to label these arrows.
Okay.
So if we attack to arrow 1, put an NH2 here, gives us a negative charge there, we just do a proton transfer to protonate it. I could have color coded these two, but purple draws so much better. If we attack arrow 2, which is actually the same as this one, right? Because we put the nitrogen para to one carbon and meta to the other. This nitrogen is still para to one carbon and meta to the other. But we do get one more possibility. We put our nitrogen there. In all three cases, the next step is just a quick proton transfer step. Right, so our two possible products are we put an NH2 here or we put an NH2 here. Or there, but that's the same as that. You can see why we didn't tackle this chapter until after we've gotten better at our mechanisms.
Yeah.
Because these aren't too bad, but if you didn't have the background that we did last quarter, it seemed like a lot. It's still a lot, but it's doable.
Yeah. We've done worse at this.
We've done worse at this point, exactly. At least there's no metals involved
Yeah. Or pops.
or epoxies.
Can you see like part this not in my. Like,
You want to leave that?
yeah, I'm just still ready.
Yeah. This is our last slide that we're going to do today. So I'll leave it up there as long as you want.
Because that's the last step. Well, for this whole thing.
Yep.
Okay.
Did it. End of week 3, we covered 2 chapters
Yeah.
and 2 fairly dense conceptual chapters because resonance is not easy.
Do we keep learning at this one say this little time or at one point are we done with each practice?
You learned all the tools that you need. So it should feel like practice, but we're gonna keep adding volume, but that's why you get more and more cheat sheets. So your cheat sheet for the midterm will be 1 extra sheet of paper.
Okay.
So you get the two sides of paper that you've already done. And you get to add 1 more. And then we'll do 2 full sheets front and back for the finals. Because it really is all the same, and at a certain point, it's just memorization, and we don't need to test memorization that much at this point. All right, so let's take a quick break. And I'll open up lab, and we can start working on finishing that up. And I'll work on writing a quiz.
Wait, should we be over like 10 minutes?
Yeah.
Right. He is walking to the gym. All right. So I can, oh, I'm walking off here, so